All right, so let's put this to the test. Our source material lays out a really simple experiment. We're going to take a standard transistor and feed it the exact kind of tiny electrical signal it's supposed to work with. So, what do you think is going to happen? Let's find out. So, here's the puzzle we're going to solve together. We've got our transistor, it's all set up, and it's ready to amplify a signal. But there's a catch, right? We're about to hit a brick wall, and the big question is, why? Okay, let's get specific about the signal. Just imagine speaking into a microphone. The sound of your voice gets turned into this tiny, fluctuating electrical signal. Our source tells us this signal is incredibly weak. I mean, it's swinging between just plus and minus 0.05 volts. This is exactly the kind of faint whisper a transistor is supposed to hear and make louder. So we feed this whisper into the transistor's input, and we're expecting a much bigger version to come out the other side. And the result? Yeah, absolutely nothing. A flat line. The output current is 0. The transistor just sits there, completely ignoring our signal. It's like it's fast asleep. So what went wrong? Well, the transistor isn't broken. It's just unprepared. Turns out, to get any useful work out of it, we first have to push it into this special state called the active region. You can think of this as its operational sweet spot. It's the zone where all the magic actually happens. And the technique to get it there? It's called biasing. And the idea is actually pretty simple. It's just the process of applying a small, steady voltage to get the transistor ready for action. You know, a good way to think about it is like a sprinter. They don't start a race just standing still, right? They get into the starting blocks, totally poised and ready to go. Biasing is what puts the transistor in its starting blocks. So what's the magic number? Well, for a typical silicon transistor, as our source material explains, it's about positive 0.7 volts. By applying this small, constant DC voltage to its input, we basically wake the transistor up and get it listening for our signal. And this 0.7 volts, that's the key that unlocks everything. See, without it, the transistor is in what's called cutoff, which basically means it's completely off. Now, if you give it way too much voltage, it goes into saturation. It's fully on, like a closed gate. But that perfect 0.7 volt bias puts it right in the middle, in the active region. It's not on, it's not off, it's listening. It's perfectly primed to amplify. Okay, so we know we need to apply this wake-up voltage, but how do we actually do it in a real circuit? Well, the source material points out two common methods, and they represent a classic engineering trade-off. You're choosing between simplicity and stability. There are two main ways to go about this. The first one, the base resistor method, is super simple to set up, but it can be a little unreliable, kind of like tuning an old radio. The second method, the potential divider, is a bit more complex, sure, but it is rock solid. And for most serious applications, stability is always going to win over simplicity. So we solved the problem. Our transistor is biased, it's awake, and it's ready to get to work. So what can we do with it? Well, its first superpower is that it can act as a nearly perfect, incredibly fast electronic switch. The logic here is just brilliantly simple. If we apply a very low bias voltage, let's say less than half a volt, we put the transistor right back into that cutoff state. The results? The switch is off. But if we apply a high enough bias voltage, we push it all the way into saturation. And just like that, the switch is on. We can flip between these states millions, even billions of times a second. But switching is only half the story. The other, and maybe the most famous, application unlocked by proper biasing is its ability to act as a mighty amplifier, taking a tiny, weak signal and making it powerful. And this is just the perfect example of why we need it. Our source material puts it perfectly. Amplification is essential to get a loud sound from a weak electrical signal produced when speaking to a microphone. Without it, your voice would never make it from the mic to the speakers. So let's see this in action. Our source gives a perfect example. We start with a tiny signal from a microphone, measuring just 10 millivolts. To put that in perspective, that's 1/100th of a single volt. It's practically just electronic noise. We feed this whisper of a signal into our properly biased transistor. And what comes out the other side? This, a powerful 400 millivolts. I mean, just take a second to appreciate that leap. From 10 all the way up to 400. That is a voltage gain of 40 times. And our source notes this is very typical for a simple amplifier. We took a signal that was barely there and made it shout. That is the power of a properly biased transistor. So let's bring it all together. We started with a problem, a transistor that was deaf to the small signals it's supposed to handle. We found the solution, biasing. By giving it that tiny, constant 0.7-volt wake-up call, we push it into its active region. And that one simple act unlocks its two superpowers, acting as a lightning-fast switch and as a powerful amplifier. This isn't just some clever trick. It is the fundamental secret that makes all of our modern electronics possible. This simple act of waking up the transistor is what lets us build everything from our smartphones to the computers that guide spaceships. It's just a tiny little component with a universe of potential. Which leaves us with one final thought. Now that its power is unlocked, what will it build next?